we started looking at the correlation of u prime v prime, and then we made a very basic physical discussion inside the shear layer, and we said that this u prime v prime bar is just a reminder from previous week. We said that u prime v prime bar is always negative. So this fact of u prime v prime is always negative most of the times. Actually, this has an impact on the energy cascade. What is energy cascade? We said that energy is flowing from large eddies or large bulk of fluids to the small ones, and then it will be dissipated. We call this as energy cascade. And this u prime v prime bar, negative sign of u prime v prime bar, has impact on the energy cascade. And in order to understand and see this effect, we will have to go to energetics. Energetics meaning that the general understanding of the energy interaction between the mean flow and the turbulence. So you have to keep it in mind that there is always a mean flow. So what we have in here, and the turbulence is actually uh, kind of uh, rides on this mean flow. So you have some sort of background flow as your mean flow, and turbulence is added to this mean flow. So we need to first of all see the energetics of both mean flow and turbulence. Actually, mean flow loses some of the energy containing energy inside to through this energy cascade. So how does it happen? We will go through this mechanism today. So a short version of momentum equation, you see it in here. So this is a very short version of momentum equation, and actually this is the momentum conservation. And uh, what do I want in here? I want energy, right? I'm talking about the flow of energy. I want to discuss about the energy, so I I I want energy. So what's the conservation equation? Not for the velocity, but for the kinetic energy of the mean flow. Actually, I want to obtain something rather than ui prime. I want to obtain the kinetic energy. Remember, the kinetic energy is ui prime squared, right? This is the mean kinetic energy. I will write it as mke, the same thing that I have in here, mean kinetic energy. So it's, you remember from your school that kinetic energy is 1 over 2 mv squared, right? 1 over 2 mv squared. So kinetic energy per unit mass is half of v squared. And if I'm talking about the mean flow, I have to put u I prime instead of v in here. So this is the mean velocity of the flow squared. So I have 1 over 2 ui prime ui bar squared. So how do I actually obtain this from the momentum equation? It's easy, because when you have the ui bar in the mean momentum equation, if you multiply it by 1 ui bar, the multiply this equation by ui bar, you can obtain the let's say rearranging it, you can obtain the kinetic energy of the mean flow. So again, you have to note that there is a difference between turbulent kinetic energy and mean kinetic energy. You remember that we said we have big eddies, these will give their energy to a small eddies and the smallest eddies. So what you have on top of the big eddies is the mean flow. Okay, so all those eddies are inside the mean flow, are embedded inside the mean flow. So what an eddy does is to get some energy from mean flow, and then it, let's say, gives it to a smaller and smaller and smaller eddies, and this eddy will be dissipated. So what you have as turbulent kinetic energy, this TKE, is the energy inside the eddies. So this energy inside the eddies, within the eddies, is called turbulent kinetic energy. But the mean kinetic energy is the energy of the mean flow. So you are seeing the definitions, the mathematical definitions. It is defined by ui bar squared. This is defined by ui prime squared bar. So it's defined by the fluctuations, and these fluctuations are due to the eddies. So this equation, when you write this equation and you multiply, I say you multiply, not, we don't talk about turbulent kinetic energy right now. We will go to that part. Right now we are talking about the mean flow. So mean flow, you are multiplying ui bar by the momentum equation, and then you will end up with this equation in here. So it is the conservation equation for kinetic energy of the mean flow, right? The kinetic energy of the mean flow. The left-hand side in here, as you can see, is the time rate of change of mean kinetic energy. So the whole time rate means ddt, d capital D over dt. So it is substantial or total derivative of mean kinetic energy. And the left-hand side, actually, this ddt tells me that the mean kinetic energy will be changing with time. Okay, d dt. And as a fluid particle moves in a turbulent flow field, this time change could be due to either unsteadiness, so partial t, and meaning even if the particle is not moving, if it is not moving and is staying at its place, it can change its kinetic energy due to unsteady motion, so the partial t. Or if the flow is steady, so if there is no partial t, due to the fact that if the particle is moving from a lower kinetic energy region to a higher kinetic region, it will change its kinetic energy. That's this thing that we know it as the convection. Okay, so there is a convection part, there is the unsteadiness part. The total is the total derivative or substantial derivative of kinetic energy. So what actually changes this kinetic energy? The answer is the right hand side. So we also can um, change this right hand side. So we are going to play with this right hand side. So if I change the right hand side as this, so I will change it. It's the multiplication of ui bar with ddxj of tau ij bar. So this tau is the shear. So I will write it as this. Okay, this part. You will see, because you can take this ui bar inside, and then if you take the derivative of this multiplication, you have to take out this thing. So it's the same thing. So let's use the open form of the stress tensor. This stress tensor is just a closed form, so use the stress as pressure plus viscosity and plus Reynolds stress. So all the stresses, let's use them. When you expand it, you will come up with this equation, the second equation. So everything is the same. So this is the total derivative. Uh, this the left hand side is the total derivative. Only the right hand side I will expand this tau ij from here and here. Okay, I will write it as the pressure term plus viscous force plus the Reinholz stress forces. So on the right hand side, I have actually term 1 and term 2, term 3, and this is the fourth term. So they are causing the change of kinetic energy, okay, in the mean flow, okay. The kinetic energy of the mean flow is changed due to this term 1, 2, and 3 and 4. So if I divide everything by density, if I cancel out density from here and all of those, I will obtain this final equation in here. Now I want to go term by term and see what are these 1, 2, 3, and 4 terms. So the term 1. So this is the exactly the same equation that I have obtained, and I divided everything by density, by rho. This is called conservation equation for kinetic energy of the mean flow. So this is the kinetic energy of the mean flow. Term 1. In general, in any equation where we can take into parentheses a collection of stress into ddxj parentheses, these are generally known as flux divergence. Okay, so ddxj of some stress inside, it's called the flux divergence. The effect of these terms that are written in flux divergence form, physically they do not cause any production or dissipation. So that the physical quantity that is on the left hand side, that is our mean kinetic energy, in the flux divergence term is not changing by production or dissipation. But what this flux divergence term do is to actually transfer of fluxes. Meaning that, for example, if inside your room there is a turbulent flow field and there is a fixed level of mean kinetic energy, if you want to increase this mean kinetic energy level, you have to do something. You have to put energy from outside. If you don't do anything, the level of mean kinetic energy can also decrease. But the term 1, which is flux divergence term, does not contribute to increasing or decreasing of the energy level. Actually, this term just transports some of the energy from, for example, one corner of your room to the other corner of the room. And generally, diffusing the energy level within the existing total energy level. So no production or dissipation happens. We say it helps to redistribute, redistribute the existing energy level. So we call it a redistribution term. This term can only transport or redistribute energy from one region to the other region, but it cannot generate or dissipate any energy. So you have to always keep in mind that when you have ddxj of some term, it is the flux divergence, and the task of the flux divergence is to redistribute the quantity inside. Okay, let's go to term 2. Actually, term 2 is 0. Why is it 0? Can anyone tell me? Yes, because you have actually P bar, then delta ij dui bar dxj, and we said that this delta ij, canonical delta, is just there to change the indices. So it changed index j to I, meaning that this j will be changed to I, so you will have dui dxi, which is the continuity equation for compressible flow. So the continuity, meaning that this will become 0. So term 2 is 0. Do we have any questions so far?
No.
Okay, term 3. So are you following? What do I started to do is to just uh, generate an equation for the mean flow. Okay, how did I start it? I started with the mean momentum equation. I multiplied mean momentum equation by ui prime, and then I rearranged it, and I ended up with this equation, the whole equation. The whole equation says that, okay, this mean flow kinetic energy is changing. How does it change? It changes due to four terms. And so far we talked about the first term, flux divergence term, and the second term, which is automatically is zero for incompressible fluid. Now the third term. The third term, we call it as viscous dissipation of mean kinetic energy. So as you see, this third term in here, we have the strain rate tensor. This is a strain rate tensor multiplied by mean velocity gradient. Actually, this is another tensor. So tensor times tensor. So both of these are second order tensors, and we have shown that before. If you remember, you can write this uh, velocity gradient tensor as the summation of symmetric part and asymmetric or anti-symmetric part. So the symmetric part, we call it Sij. The antisymmetric part, we call it omega ij. And if you put this inside the term 3, you will find term 3 equal to minus 2 times kinematic viscosity nu times Sij times Sij plus omega. And then it will be equal to minus 2 nu Sij. So where this omega goes, can anyone tell me? Where is this? Okay. Uh, Previously, I asked you to do some exercise and show that multiplication of a symmetric tensor by an asymmetric tensor or anti-symmetric tensor will be zero. So you can prove it that the multiplication of these two will be zero. So this is interesting. This thing is interesting because in this term, which includes your viscosity, there is your viscosity, you are multiplying Sij with itself in here. So you have two new Sij bar, Sij bar. Actually, two new Sij bar, Sij bar, this thing is always positive. It can never be negative because you are talking about the square of Sij, okay? And multiplying with 2 multiplying with nu. So these are all positive, so everything is positive. And there is a minus sign in the front of it. So the whole term will always be negative. So this term 3 with its minus sign will always be negative. This means no matter what kind of flow you are interested in, this term 3, will always cause reduction of mean kinetic energy. So we said that the mean kinetic energy is changing left hand side. What causes this change are at right hand side. So the term 3 in here is always negative, meaning that it will always cause reduction of mean kinetic energy. So we say it will act as a sink. So it's not a source, it is a sink. It will drain mean kinetic energy. Physically, this is actually the loss of mean kinetic energy due to, as you can guess, viscosity or viscous effects or friction, and it is directly converted to heat. So, because of the friction, your mean kinetic energy is directly converted to heat. So we call it as a viscous dissipation of mean kinetic energy because it is because of viscosity or friction. Okay, the last term 4 in here, what we have. Actually, we call this term as a loss of mean kinetic energy to turbulence. Why? We will see it. You, if you use similar argument as above, I mean, put again the mean velocity gradient equal to symmetric part plus anti-symmetric part. You can rewrite the term 4 equal to this. Okay, so it is ui prime uj prime bar times mean strain rate Sij bar. Because we know that the Reynolds stress tensor, this ui prime uj prime bar, is also symmetric, and when you multiply it with omega, which is anti-symmetric, it will be 0. So this last equation is also interesting. The, first of all, this term does not have a minus sign. You see, it is positive. In most of the shear flows, ui prime, uj prime bar, and uh, let's say Sij bar have different signs. Most of the shear flows. So usually in most of the shear flows, this will be negative. So this means that we have another negative term in, let's say, on the right hand side of mean kinetic energy equation. And this term, number 4, also behave towards reducing mean kinetic energy. But unlike this term 3 in here, unlike this term 3 in which the kinetic energy goes into heat. So it goes into heat because of, we said, viscosity. Unlike term 3, in term 4, you lose mean kinetic energy, but this mean kinetic energy doesn't go to heat. It goes into generation of turbulence kinetic energy. So when in a moment when we start talking about energetics of the turbulent flow, you will see exactly the same term inside the energetics of the turbulent flow with the minus sign. So when we write the conservation equation for the turbulent kinetic energy, you will see this. So this term 4 drains the mean kinetic energy and then gives it or feeds the turbulent kinetic energy. And that's the connection between the mean flow and turbulent flow. And as I said, we call this term as a loss of mean kinetic energy to turbulence. So as you see, physically we showed something. We showed those eddies that are getting smaller and smaller and smaller, and we said that okay, there is a mean flow on top of those eddies, and the energy comes from the mean flow to the eddies, and then through the cascade of energy it goes and then it's dissipated into heat. And in here, by the by using the equations, mathematical equations, also we are showing the same thing. So this is the part that is responsible for draining kinetic energy from mean flow and feeding it into the turbulence. Okay, no questions? Can I jump into the energetics of the turbulent flow right now? So what I want to discuss about the turbulent flow. So we are going to do exactly the same procedure for the turbulent flow. So my goal is to obtain conservation equation for turbulent kinetic energy, which I call it as K. This is turbulent kinetic energy. So you have to follow again the similar steps. So I just wrote these steps in here for you. You have to start from instantaneous momentum equation this time, not the mean momentum equation. So write the instantaneous momentum equation, decompose the instantaneous momentum equation, meaning that you have ui equal to ui bar plus ui prime. After you decompose it, you have to subtract mean momentum equation to get the fluctuations conservation equation. So you already have your mean momentum equation. And when you do this and subtract the mean momentum from this, you will end up with only fluctuation conservation equations. What I mean is that after writing this, after finishing the step 2, you have to end up with something like this. dui prime dt is equal to something. It's about the fluctuations only. Now that we have the fluctuations, I can multiply everything by the fluctuation itself. So when I multiply it by fluctuation and then average it, it means that I will get ddt of ui prime squared bar. So after averaging. So first I have to multiply it, so I will come up with ui prime squared. Then averaging means ui prime squared bar. And ui prime squared bar is nothing but your turbulent kinetic energy. So what I have in here is uh, ddt of actually 1 over 2 of ui prime bar equals to something. Mean right hand side of your equation. So we call this as actually this is the final equation that I just wrote here for you, and it's the conservation equation, or we call it conservation equation or the transport equation. Both of them are true. Conservation or transport equation for turbulent kinetic energy. So this is the final equation that looks like this. So again, if you compare it with the mean flow, okay, at the left-hand side, you see that you see ddt of your turbulent kinetic energy, meaning that your turbulent kinetic energy is changing through time by what means? By this means, by either 1 or 2 or 3. So we're gonna look at these three terms as follows. So I have the same equation in here just for you to be able to follow. So term 1 again, I call it the redistribution of K or diffusion of K. So as I said, it's a flux divergence term. And as you might guess, similar to what we had for mean kinetic energy, this represents again the redistribution effect. There will be an existing level of turbulent kinetic energy in the flow field, and because of the fluctuations of velocities, pressure, and viscous effects, the turbulent kinetic energy will move will move around. So you have the fluctuations, velocity fluctuations, you have pressure fluctuation, you have the viscosity effect. Because of these, you are actually diffusing or redistributing kinetic, turbulent kinetic energy. So it will get redistributed. Similar to mean kinetic energy, this term 1, will not contribute to any generation or destruction of turbulent kinetic energy. It only redistributes it. So term 2 in here, and I call it the production of K. If you compare it to term actually 4, to compare it to this term 4 in the mean kinetic energy, it's exactly the same. See, ui prime uj prime bar times dui bar dxj, and this is exactly the same, right? Only the sign is different. This is positive in here, this is negative in here. And if you remember our discussion in mean kinetic energy, we said in most shear flows, the stress is negatively correlated with the velocity gradient. So we said that the multiplication is always negative. This term will always be negative in mean kinetic energy. And we said that it shows the drain or loss of mean kinetic energy. Here, in turbulent kinetic energy, in the first equation, this term has a minus sign, as you see. And it means that it is always positive. The whole thing is always positive. What does it mean? Meaning that there will be a term that is going to be always positive in the right-hand side of the K equation, turbulent kinetic energy equation. And this means that whatever this term is, that we call it as production, it is always contributing to the production of new turbulent kinetic energy. Therefore, we call it production of K. So this production is very important. Actually, you can show that this term, as you have in here, you can again decompose this mean velocity gradient into symmetric and asymmetric part, and then you can show that it is equal to this, what we shown before. And then you can show that if Aij is ui prime uj prime bar minus 2/3 of turbulent kinetic energy, this will be equal to minus Aij bar Sij bar. So it is used, the definition of anisotropic part of the Reynolds stress tensor is used. In other words, the only component that is responsible for generation or production of turbulence is the anisotropic part of the Reynolds stress tensor. So this A is the anisotropic part of this. So if you remember, the trace of Aij was Aii, and it was equal to 0. So can you show this, the trace of Aij will be 0 if you decompose the Reynolds stress tensor into isotropic and isotropic parts. Remember, you had this um, ui prime uj prime bar was equal to Aij plus 2/3 of k delta ij. So if you put this inside this equation, you will obtain, uh, let's say, you will obtain this term equal to P, and then you can show that your production is minus Aij bar, Sij bar. So basically, if you use this definition of decomposing the Reynolds stress tensor into symmetric and asymmetric part, you can show that the production of turbulent kinetic energy, meaning this part, this is the production, is only because of the anisotropic part of the Reynolds stress tensor. It's only because of the Aij bar.